I'm Father Robert Balacer, the Digital Jesuit, host of TWIET, This Week in Enterprise Tech on the TWIT Network, and you've stumbled into another edition of Stuff My IT Guy Says. As you can see behind me, I am at the Interop Hot Stage Warehouse here in, well, a super secret space of California, getting ready for the show in Las Vegas. But sitting next to me is, well, software engineer extraordinaire, Evan Poncelet. Evan, thank you very much for talking to us.
Hi, Robert.
You're going to explain a phenomenon that, well, we hold dear to our heart whenever we're testing our network, and that is OTDR. For the folks playing at home, what is OTDR?
OTDR stands for Optical Time Domain Reflectometer.
Okay, that sounds like a bunch of made-up words there. Right. Put those together. What's that supposed to mean to me?
Right. So what that's the study of is what happens to light as it transmits down a cable, a fiber optic cable. And so it's following a physical phenomenon where you're transmitting a pulse of energy. And so it actually is transmitted as a wave. And when it reflects back to you, you can tell a number of different things have occurred on the channel just by analyzing carefully what you see and when you sent it.
Now, one of the important things to realize about OTDR and any equipment that uses the phenomenon is that the same side that is sending the light is also going to be receiving the light back. It reflects.
Yes.
Why does it reflect?
Right, so the reflection is caused by an index of refraction mismatch.
Got it.
And so that's actually the same thing that allows you to have fiber optics, is there's an index of refraction mismatch between the core, which is where the light's actually transmitted, and the cladding which surrounds it. So what you're seeing here is actually the jacket of the cable, but within that there's the cladding, and then within that cladding there's the core.
Right.
And so that index of refraction mismatch between the cladding and the core results in something called total internal reflection. And that's the light pipe phenomenon.
The fact that we have multiple types of material in here means, as we know, waves are going to move through materials at different rates. Light doesn't move through the cladding as fast as it moves through the core, and so you will get that natural reflection of light. And with that reflection of light, you can tell what?
So with that reflection of light, you can tell the length of the cable, because you know the nominal velocity of propagation of the light traveling through the core, which is fused quartz. And so if you know the time that you sent it and how fast you sent it, then you know that if you multiply those two things together, you get the distance that it's taken. So that's actually the round trip distance back and forth. So you have that and you get the length of the cable. Also from that you can study certain things like there's a phenomenon called Rayleigh scattering. And what that is a measure of how much of the light that's transmitted is being reflected back at you from just the individual particles within the fused quartz. So there's also a phenomenon of loss, and so that's the instantaneous or the a discontinuity that results in that light being diffused, kind of like a lampshade diffuses normal light that you see in a normal household lamp. And then there's also a phenomenon called attenuation, and so that's the gradual loss of intensity of the light as it travels down the cable. And so in this case, just to provide kind of a spot example, this is attenuating the light from the camera that I'm seeing right now. And so that's good for my eyes because I'm not damaging my sensitive optical equipment here, but that's bad for your network because you want intense light so that you can receive that.
Right. Now all of this sounds good on the theoretical level. I mean, we like to know what light is doing as it's traveling through our fiber plant.
Yes.
But what kind of data can I take from that? I remember at one point there was another fluke engineer who was showing me how just by bending the fiber, he could change the light return, and therefore you could make inferences about what was going on with your network.
Yes, that's exactly true. So bending the light actually, or bending the cable, results in leakage of light. So with the cable itself, there's a certain critical bend that you can induce, and once it goes past that angle, light will actually leak out of the jacket. And so you want to avoid most bends in cables, and that's not to say that it has to run perfectly straight, but you want to avoid any kind of small kinks within it past a certain radius, which is usually around the size of a dime. If you're bending past the radius of a dime, then you're probably coming into problems.
Right. Another big advantage of using OTDR equipment is that I can tell if there's a break.
Yes.
Like for example, if I know I have a 300-meter run of fiber, and my OTDR equipment is telling me, oh, I've only seen 100 meters of fiber here, you know that somewhere along the line, in fact, at 100 meters, you've got something wrong with your fiber plant.
Yes, and so that can be very helpful for long runs of fiber, but it can also be very helpful in a data center environment. And so what you'll need, so there's little small issues with that, and that you can tell when there's a break, but you can also tell when two cables have been spliced together poorly. And so poor splices can result in all kinds of issues, and breaks can result in all kinds of issues as well. And so the number one is that reflectance. So there's that index of refraction mismatch between the air in this case and the break, or just the discontinuity of the broken glass that causes that light to leak out. And so what we can do is measure the distance to that fault so that you don't have to go through with a visual fault locator or a red laser or something like this and find where that light's spilling out. You can just attach your instrument, here in this case an OTDR, and detect exactly where that break was. And you can also characterize that break. So you can tell if it actually is a break, or if someone has gone through and used a fusion splicer to melt the two ends of the glass together, or a mechanical splice where they're just using a small mechanical device to hold the two together very closely.
Right, absolutely great pro tip. Now they can find out more about OTDR by just, well, going anywhere. In fact, if you go to the Wikipedia page, funny thing, the tools that are shown on the Wikipedia page for OTDR, well, any guess what company they might belong to?
Fluke Networks.
They might belong to Fluke, that's right. But where, if they wanted to find out more about your gear and the phenomenon of OTDR, where should they go on the web to find out more about Fluke?
Right, so www.flukenetworks.com, we have a products page that actually goes into detail. We have a lot of different product demonstrations, and I think there's also a virtual guide to our OTDR. And we talk about all the different type of events that can go on, the different TIA standards that govern how many connectors you can have in series on a link, and just all kinds of phenomena, and how to read an OTDR trace, which many people find difficult, but we've also included features to make that a little simpler for network engineers.
We're going to be taking a look at this bad boy at sometime in the near future, but until then, Evan, thank you very much for coming on to talk to me.
Thanks very much, Mark.
And you stay tuned, because that's not the last bit of stuff on IT Guys.